Our next chapter deals with Newton's laws of motion. Now, most of you have probably already heard about Newton before. It's actually Sir Isaac Newton. He was knighted, and he is considered by many people to be the greatest physicist of all time. He's basically the guy who invented physics as a modern science. He did so many things, there are just too many to list, but a few of his major accomplishments were that he invented calculus, which is an advanced form of mathematics necessary for doing advanced types of physics. He made major contributions to many areas of physics, including the physics of motion, astrophysics, the study of light and color, and thermophysics, and many areas of physics. Sir Isaac Newton made major contributions to those areas of physics. And he actually wrote a book summarizing all of his discoveries, and that book is called the Principia. The name comes from Latin. It was originally written in Latin, but it basically laid out the foundations of physics, and it's considered one of the most important scientific works ever written. And in the Principia, Sir Isaac Newton actually formulated the 3 laws of motion that we're going to be talking about in this lecture. Now, Newton's first law of motion, I've kind of typed out the way it's written in your book, and most books give it the same kind of definition. It says, every object continues in its state of rest, or its uniform, that means constant speed, straight line motion, until acted upon by a non-zero external force. If you took physics in high school and you learned it that way, or it's in your book and you just like it and you understand it, that's great, use it, perfectly fine. But I often actually, in my classes, I like to formulate the first law a little bit differently. And the way I say the first law is this: to accelerate an object, you must apply a net external force. Now, we've talked about what acceleration means. Acceleration is equal to a change in velocity over a change in time. And remember that little triangle means change in. So, we also need to remember that velocity is a vector quantity. That means its direction is important. So if we want to change the velocity, i.e., if we want to accelerate something, we can either change its amount, that is, speed it up or slow it down, that's changing how fast it's going, or make it turn. In other words, change which direction it's going. If you do either of those things, if you change how fast it's going, i.e. speed up or slow down, or change the direction it's going, i.e. turn, you're accelerating. So the stuff in the parentheses is just to remind you what it means to accelerate something, but the actual formulation of the second law is this, and I think it's a lot easier to remember. To accelerate something, you must apply a net force, a net external force. And that is Newton's first law of motion. Now, we have previously described inertia as a resistance to force. If I push on something, its mass resists the change in motion caused by that force. A bigger mass, you get less acceleration. Well, that principle of inertia applies directly here. So that's why Newton's first law is often referred to as the law of inertia. And I think the reason for that will be a little bit more clear if we look at some examples of how the first law can be applied. But as we work through these conceptual examples that we're going to look at for applying the first law of motion, keep in mind the basic idea of inertia. Things want to keep whatever motion they have. If they're moving in a straight line, they want to keep moving in a straight line. If they're just sitting there, they want to keep just sitting there. In order to change how something is moving, you have to apply a force. So this is our big idea. Things want to keep whatever motion they have, and to change the motion, you need a force. So let's look at some examples. Here we see an image showing inertia in action, and we can see how this applies to our first law of motion. This is, of course, a depiction of the very famous magic trick where you have a place setting on top of a table underneath a tablecloth, And if you jerk the tablecloth fast enough, you'll pull the tablecloth away, but the place setting will remain on the table. Now, if you pull the tablecloth really slowly, it will drag all these things, the plate, the goblet, the candle, the silverware, anything that's there, it'll be dragged onto the floor with the tablecloth. But if you jerk it fast enough, you can actually pull the tablecloth out from underneath these objects. How does that work? What does that have to do with inertia? Let's think about what happens when you pull the tablecloth out slowly. The plates and the goblet and everything else, they're sitting on the tablecloth, and as you start slowly dragging the tablecloth away, the friction between the plates and the tablecloth is gripping these place-setting objects and pulling them away. And if the acceleration is small, then the friction has enough force that it can keep these on the tablecloth and drag with the tablecloth. But friction has a maximum value. So if you really jerk the tablecloth away, the tablecloth cannot provide enough friction to pull these guys with it. In other words, the friction cannot apply enough force to these guys to accelerate them as fast as you're accelerating the tablecloth as you pull it out. And so, what does the first law tell us? What does inertia tell us? It tells us that things want to keep the motion they have. And so these guys are initially just sitting here. That's their motion. They're not moving at all. They're just sitting there. That's what they want to keep doing. They want to just keep sitting there. And if you don't have enough force to accelerate them as fast as the tablecloth is being accelerated, they're just going to keep sitting there. Now over on the right, we have another example that is kind of one that's common in our everyday experience. If you've ever been driving your car and maybe going a little bit faster than you should have, and something's out in front of you and you have to slam on your brakes, what happens to you? You feel like you're thrown to the front of the car, like you're tossed towards the steering wheel. But that's not what actually is happening. What actually is happening is you and the car are moving together. You both have a velocity. And then when you hit the brakes, the car starts to slow down, but you keep the velocity that you have, and so you continue to move forward. And so inside the car, it feels like there's some force pulling you forward, but actually, you're just keeping the same motion you already had, because things want to keep the motion they have. And so the car is slowing down out from underneath you, you seem to move forward. Now, if you brake slowly instead of slamming on your brakes, the friction between the car seat and the seat of your pants is enough to slow you down with the car. And so you don't get thrown forward. But if the acceleration is very big, if you're slamming on your brakes, the friction is not strong enough to hold you in place, and so you get thrown forward. Let's look at a few more examples of inertia. So here we have this ball, and you can see there's a thin string tied to the top of the ball, and a second thin string tied to the bottom of the ball. And if you pull the two strings until they break, it turns out that you can break one string and not the other, and which string you break depends on how you pull. If you pull slowly, then the top string is the one that will break. But if you pull quickly with a jerk, then the bottom string will break. Why do you think that is? I think we're talking about inertia here. So what does inertia mean? Before you start pulling, the ball is just sitting there. And so the ball wants to keep the motion it has. It just wants to keep sitting there. And so if you jerk, the inertia of the ball is going to hold it in place, and that force is not going to get transmitted to the top string, and the bottom string is the one that will break. But if you pull slowly, you can overcome the inertia of the top of the ball, and then that force gets transmitted to the top string, and that's the one that breaks. Because it's feeling both the weight of the ball plus the force that you're pulling down with. And in that case, the top string will break. In this next image here, this is sort of a classic physics demonstration. You have an index card over a cup, and there's a quarter or some coin on top of the index card, and you just flick it with your finger and knock the index card out, and what happens is the index card goes away and the coin will fall into the cup. And this is very similar to the tablecloth trick that we talked about in the last slide. If you flick the card so that it accelerates very quickly, the friction of the card and the coin is not enough to move the coin with that high acceleration, and so the coin just wants to stay where it is, and when the card is no longer underneath it to support it, it falls into the cup. And then the last image in this slide is a hammer, and you can see that basically you've taken the whole hammer and you're slamming it into this wooden block, the butt of the hammer slammed down into this wooden block, and that'll actually tighten the head on the handle of the hammer. Because at first, when you're slamming it down, both the handle and the metal part of the hammer are moving together, but once the handle strikes the wooden block, the handle is stopped, but the metal part still wants to keep moving downward, and so it pushes against the handle and tightens down further. In ancient times, they used to think that the Earth was fixed and the sun and all the planets rotated around the Earth. But later in the 1500s, a guy named Nicholas Copernicus proposed an alternate explanation to describe the motion of things in the sky. He proposed that the Earth goes around the sun and it rotates around its own axis. So spinning on its own axis is what gives the appearance of the sun moving across the sky and provides for day and night. And of course, the Earth going around the sun was a much simpler way of looking at things. And as we know now, it turns out to be the correct way of looking at things, because that's what really happens. The Earth really does go around the sun. But when Copernicus first proposed this theory, a lot of people were very hesitant to accept it. And one of the arguments that they made against it was the argument of how a bird could catch a worm. And so the idea was this: if the Earth is rapidly moving around the sun and rapidly rotating about its own axis, if there's a bird on the tree limb and there's a worm underneath that the bird wants, well, what the bird could do is just simply drop down and catch the worm. But the argument went, if the Earth and the worm and the tree were moving very, very fast, when the bird dropped down, the tree and the worm would be carried away and the bird would not be able to catch the worm. But of course, we know that things always want to keep the same motion they have. And so the bird and the tree and the worm are all moving together as the Earth moves. And so when the bird drops down, yes, the worm is moving that way very fast, the tree is moving that way very fast, but the bird is also moving that way very fast, and they're all moving in sync with one another. So when the bird does drop down, the worm doesn't get carried away because the bird maintains that sideways motion as it's falling down. And again, that's just a basic idea of inertia, or Newton's first law. Now, the way I told you that I like to say the first law was to accelerate something, you have to apply a net external force. The second law, Newton's second law, tells us how much acceleration you get. So the first law says in order to get an acceleration, you have to apply a force. The second law tells you, here's a formula, we can calculate how much we get. And the formula says the acceleration you get is the net force that you apply divided by the mass. Now, we have that the acceleration is equal to the force divided by the mass. And we can write that out as a formula. And we can apply that formula to each of the situations that we see in this figure here. So, looking at the left figure, figure 2.7, we have a hand pushing against a brick. And so this hand is applying some force F, and the brick has some mass M. And if we divide the force by the mass, that will tell us the acceleration. Now, what's going to happen if I double the force? So now you can see in the picture I've got two hands pushing on the brick, and so I have doubled the force. And so I can put a 2 in front of the F, and the force has gone up twice as much. But there's a thing about equations. If you do it to the right-hand side, you got to do it to the left-hand side. So guess what happens? If I double the force, I get twice the acceleration. And that's what we see here. If you have twice as much force, you get twice as much acceleration. Now, what happens if I double the mass again? So now I've got two hands pushing, so that gives me twice the force, but now I'm going to be dividing by twice the mass. And so if I add in 2 in front of the m here, I can say that the 2's are going to cancel there, and I go back to the original acceleration. And so what we see is that twice the force on twice the mass gives us our original acceleration. What that tells us is that the force is proportional to the acceleration. The bigger the force for a given mass, the bigger the acceleration. But if you increase the mass, you reduce the acceleration. And we can see that in this second figure over on the right. So we go back, we've got a single force pushing on a single brick, and then if we double the mass, here I've written my equation again. If I increase the mass by 2, then I'm dividing by twice as much, and the acceleration is half as much. And that's exactly what we see here. And again, if I take that same force and I push against 3 bricks, I'm going to get 1/3 the acceleration. So every time I increase the mass, the acceleration decreases by a proportional amount. Now let's look at one of these check our understanding things from our textbook. There are a few points here we want to look at. The first one says, in the previous chapter, we defined acceleration to be the time rate of velocity change. That is, the change in velocity over the change in time. We now are saying that acceleration is the ratio of force over mass. That is, F over m. Which answer is true? And of course the answer is they're both true. They're telling you different things. The first one is telling you how the acceleration is involved with the motion, and in the second case it's telling you how the acceleration is involved with the force. But the acceleration is going to be the same in both cases. The next question says, a jumbo jet cruises at a constant velocity of 1,000 kilometers per hour when the thrusting force of its engines is a constant 100,000 newtons. The question is, what is the acceleration of the jet? And that's kind of a trick question because it tells you that the jet is moving at a constant velocity. So I've drawn my picture of a jet here, my little crude picture, and we have a constant velocity. And the question is, what's the acceleration? Well, we know that the acceleration is equal to the change in velocity over the change in time. And if the velocity is constant, that means the change in velocity is 0. It means it's not changing. And so the acceleration would be 0 in that case. And so if a jumbo jet is cruising at a constant velocity, any constant velocity, its acceleration is going to be equal to 0 meters per second squared. Now the next question says that what is the force of air resistance on the jet? That's the second part of question number 2. Well, we have the force of thrust pushing that way, and we have the force of air resistance pushing in the opposite direction. What must be true of those forces if the acceleration is 0? Remember that the acceleration is equal to F over m, but it's the sum of the forces. It's all the forces added up together. So if the acceleration is 0, what must the forces add up to be? They've got to add up to 0. And so that tells me that 100,000 newtons up here, that must also be the force of air resistance, but in the opposite direction to cancel. And then question number 3 says, suppose that you apply the same amount of force to 2 separate carts. One cart has a mass of 1 kilogram, the other cart has a mass of 2 kilograms. Which cart will accelerate more, and how much greater will the acceleration be? Well, again, we know that A is equal to F over m, And so if one cart is 1 kilogram and the other cart is 2 kilograms, the one that's 2 kilograms is going to be dividing by a bigger mass. And that means that that acceleration will be smaller. How much? By 2. Because if I'm dividing by 1 and I'm compared to dividing by 2, the answer of the second one will be half the answer of the first one. Now, previously, we talked a lot about falling objects, and we made the point that all objects, regardless of their mass, fall with an acceleration of about 10 meters per second every second, 10 meters per second squared. Aristotle said that heavier objects would fall faster than lighter objects, but experiment proves that that's not true. So, how can we explain our experimental results that all objects accelerate the same amount? And so here's the basic way to explain it, and we can explain it using Newton's second law. So here we have a block of mass m, and it's going to have a force of gravity, let's call it F, and we know that the force divided by the mass is going to equal little g, the acceleration due to gravity. Now what happens to the block that's twice as big, twice as much mass? Well, the force of gravity is going to be twice as big because it's a heavier object, but the mass is also twice as big. And so when you divide the total force by the total mass, those 2's cancel and you still get g. It doesn't matter how big the mass is because the force of gravity is going to be bigger, but the amount of mass is going to be equally bigger. And when you divide, you always get the same number, little g. This was something that for a long time, after Galileo discovered it, confused people. Why do things all fall at the same rate? Newton was able to explain that using his laws of motion. And so far we've looked at the first law and the second law. In the next video, we're going to look at the third law.